In this video, I'll walk you through the different storage modes and the packing feature of my data picker tool, part of the Game Tools Blender extension. In the previous video, I gave a brief tour of the tool and demonstrated some basic examples, like baking the XYZ position into 3 UV map channels, which required 2 UV maps. Now let's say I also want to bake the XYZ components of an axis. That would require 3 more UV channels, meaning I'd need 3 UV maps in total. The more data you bake, the more UV maps you'll need. And while a UV map doesn't cost much, it isn't free either. The overhead is predictable and measurable. Each UV map adds 2 16-bit floats per vertex, or 2 32-bit floats if full precision UVs are enabled. Adding an extra UV map is not a deal breaker. It contributes to the memory footprint of the static mesh asset, and it's bound to slightly affect memory bandwidth, but that's about it. Adding a few extra UV maps to a static mesh is generally fine. However, if you get into the habit of adding many UV maps to every asset, it can start to impact performance. At some point, relying too heavily on UV maps to store too much data just becomes impractical. And that's where packing comes in. It allows you to, pack multiple values into a single UV channel at the cost of precision. My tool lets you pack 2 floats using either a numeric method or a bitwise method. You can also pack 3 floats, again using either method. And there's also a technique that lets you pack 2 floats by using the integer and fractional parts of a single float. Let's start simple and use that last one to pack an axis along with a position. We'll bake the X and Y position, and also bake the X and Y components of the, say, right axis, whatever. Using the UV fraction storage mode, I can pick which other data layer will contain this layer, highlighted with this little arrow. So let's pack the X component of the axis with the X position, and the Y component with the Y position. This works well because the position is baked in centimeters, so subdecimal precision isn't very important. The integer part is what matters, in most use cases. That means we can discard the fractional part and replace it with the axis value remapped to the 0-1 range. Technically, though, 1.0 can't be used because its fractional part is just 0. So the axis value must actually be remapped to a range between 0 and just below 1.0. The bake report should show you which data was packed into each layer, if any. In the Vertex shader, both values can be extracted. The position can either be rounded to the nearest integer or kept as is, losing some precision in either case, since its fractional part holds the axis value which will need to be remapped. Thus, we've baked 4 values into just 2 channels. Interesting. This method is ideal when you're baking one value where the integer part matters most, and another value that fits easily into the 0-1 range without much precision loss. Typically something like a position and a unit vector, such as an axis. When baking 2 arbitrary values, other options are available. Let's now look at packing 2 floats into a single channel using numeric packing. I call this numeric because it uses arithmetic to store 2 values into one using simple math. I'll remove the axis data layers and pack the Y position with the X position instead. Since we only have 2 channels, the correct one is automatically selected as a target. And this option lets me choose in which numeric quote-unquote part the data will be baked. If I pick Y, this layer will be stored into the second part, and that other layer will be stored in the first part, and the other way around if I pick X. This packing mode results in moderate precision loss and requires 32-bit UVs, although precision is often acceptable for use cases like baking pivots for grass assets. Needless to say, packing 2 floats into a single UV map channel, thus requiring 32-bit UVs across all UV maps, can defeat the purpose of packing. In that case, it's likely preferable to store the 2 floats in 2 separate 16-bit channels instead. Packing becomes worthwhile when you can fully take advantage of 32-bit UVs by packing multiple values, if that makes sense. Anyway, the 2 values can be extracted using this material function, which is included in my content examples, and packaged as a plugin you can easily copy into your own project. Next, check the bake report or the exported XML file for the offset and range values you'll need to feed into the material function to correctly remap the data to its original range. And that's it. Sweet. Next, same idea, except this time we're packing 3 floats like an XYZ position. The loss in precision can be noticeable, to say the least, and could be a limiting factor in many use cases. For foliage assets that don't need extremely precise pivots, it's usually fine. Again, you can define the packing order using the X, Y, and Z components here. Be careful not to create conflicts, for example 2 data layers using the same component for packing. If that happens, the bake will safely fail and prompt you to fix the issue. And again, in Unreal Engine, there's a material function for unpacking the 3 values. Be sure to check the bake report or XML file for the offset and range values. These are needed to remap each value back to its original range. This material generates a spherical gradient around each object's baked pivot point. Notice that some pivots are not perfectly centered on the plane, and that's the kind of precision loss you can expect with numeric packing. These packing techniques can be used safely in either UV channel, U or V, but that's not the case for the next 2 techniques I'll demonstrate. These are called Bitwise methods because they manipulate the 32 bits of a float directly to pack the data. This makes the float's numerical representation arbitrary, so much so that it often does not survive the implicit 1- operation applied to the V channel. Because of this, it's strongly recommended to use these bitwise methods only in the U channel. The advantage, however, is significantly higher precision. Using my custom algorithm, which reserves 1 bit to avoid generating nans, packing 2 floats into a single 32-bit float yields 16 bits of precision for the first value and 15 for the second. Packing 3 floats into one 32-bit float gives you 11 bits for the first value and 10 for each of the remaining 2. That's often more than enough to store positions and local offsets for foliage assets and similar cases. The workflow is the same. Pick a layer, set it to bitwise storage mode, target the layer that will store this data, it must use UV storage mode, and make sure you target the right quote-unquote packing component, and voila. You'll then need to unpack the data in the Vertex shader using the provided material functions, which includes the following HLSL code. This is for unpacking 2 floats and 3. These floats are normalized to a 0-1 range for packing, so the material function will also need the offset and range values reported by the bake. Notice how the pivots are much more accurately centered on each plane compared to numeric packing. And that's pretty much it for packing. Really cool feature. Now, data can also be stored in Vertex colors and normals. Vertex colors offer 8-bit precision per channel and provide 4 channels total. This severely limits what's possible, but there are still useful applications. Vertex colors are best suited for storing things like a mask, typically in the alpha channel, and a unit vector, such as a normal, in the RGB channels. A simple constant bias scale remaps the unit vector components to the 0-1 range, allowing them to be quantized into 256 discrete values. 256 values isn't a lot, but it can be enough to store more general data, such as offsets or positions, depending on the value range and the required accuracy. The tool handles everything automatically. Just select Vertex color as a storage mode for something like the X, Y, Z position and you're good to go. The bake will report the range and offset values needed to remap the data back to its original scale, with moderate to high precision loss depending on the case. Now, storing data in normals is even more constrained and comes with significant caveats. Even if you store a single value, say in the X component of the normal, the entire vertex normal will be overridden. This happens due to technical reasons explained in detail in the wiki. In short, vertex normals are always normalized. This constraint is enforced at every step of the pipeline. likely during modeling in your DCC software, during export, import, and even at runtime in most game engines. This normalization means storing arbitrary values in normal components is tricky. For example, if you try to store 0.5 in the X component and 0.0 in Y and Z, the resulting vector has a length of 0.5. Upon normalization, X will become 1.0, completely changing the stored value. To get around this, the tool adjusts a second component, usually Y, so that the entire vector has a unit length, while preserving your target value in the X component after normalization. This makes it possible to store up to 2 arbitrary values in 2 components. The third component is then automatically calculated to ensure the vector remains normalized. The bake report will indicate what happened internally, whether the data was stored in all 3 components or if one value had to be discarded to ensure the first 2 remain unchanged after normalization. That said, if you're baking a unit vector, like a random direction, the tool will detect this special case and allow you to bake all 3 components, X, Y, and Z, directly into the normal. And that's it for storage modes.